Before we go and look at the two main approaches to understanding how we see the world, let's spend a moment and just note that we often think of the eye as if it were a camera, and it bears some similarity to a camera, but that analogy is potentially very misleading as well. So I'd like to just spend this video asking why the eye is and is not like a camera. So we see an eye and a camera there, we immediately notice something. They both have lenses in the front, and each lens has a small hole which allows the light to pass through into an interior. So the case of the camera is not unlike the ball of the eye, and the lens of the camera is not unlike the lens of the eye. So that suggests itself very strongly, right? Now, a camera obscura illustrates how the image is formed on the back of both the camera and the eye. Camera obscura arises if you have a darkened chamber, that's the box of the camera, or a room even, with a small hole in it. And if there's light outside, light bouncing off things like this tree here will pass through this small hole, and there will be a projection on the back of the casing, which is an inverted image of what's outside. So that in your camera, the picture that is recorded is upside down with respect to what's outside. Now, I didn't say that that's true of the eye. It's true of the eye if we regard the eye as a camera. But anything with a small hole in it could potentially act as a camera obscura. Here's a camera obscura. A lens attached to the window of a room produces an image of the outside of the room, inside the room. This is interesting. So if you darken your room, put a lens on the window, there'll be an image of the outside inside your room. But of course, your room still won't have seen anything, right? The camera obscura is a fascinating thing because small little peepholes like this occur all over the place. And you may find them occurring naturally. So when you look at a tree in the autumn, for example, if the sun is streaming through it, then the leaves, as they move, will generate thousands and thousands of tiny little images which are constantly moving. It's part of the reason that trees produce this dappling movement in autumn. The camera obscura was well known a long, long time ago, and no less a person than Leonardo da Vinci recognized that the eye must have strong similarities to a camera obscura, and he took that as a model for the eye. But he was interested in geometry and light, and he wasn't much of a physiologist. Leonardo was an unspeakable genius, but his concern was geometry. And in fact, if we look around the natural world, we find this kind of geometrical production of images everywhere. In every dewdrop, if you get down on your hands and knees and examine a dewdrop in your garden in the morning, you'll find all kinds of images inside. So light just does this. As it passes around, it generates images around the place. That's where the similarity between the camera and the eye stops. The thing about a camera is it has film or a digital sensor at the back, which must record what is projected onto it so that something else can see that image. The camera itself doesn't see. The retina does not do this. A camera is pretty useless if it's moving around because it never has time to get a purchase on an image in order to fix it. If you shake a camera around, you end up with just blur. Seeing, on the other hand, is an activity. And as we'll see, vision not only isn't bothered by movement, vision requires movement. And this is where we begin to notice that the visual system, the thing that enables seeing, is not just the eye, but it's the whole body in the world. So we'll just have a look at how movement comes into the picture. And I'm going to show a slide next. Here, we'll just show it there. Now, this won't work if you're watching this on a phone, but if you're watching this on a computer screen, make this full screen and pause the video after I finish speaking and stare at the black dot in the center without moving your eyes. You can see, while you're still moving your eyes, that there's a big gray penumbra around the black dot. But if you hold your eyes still and stare at the black dot, the gray penumbra goes away. Eventually there'll be just the black dot and an undifferentiated white background. But as soon as you move your eyes, the black dot comes back. So pause the video and try that there. See, does it work for you? It's a bit difficult to know whether these work over video. Okay, I hope you did that. So that demonstrates to you how important movement is. The gray area came back as soon as you moved your eyes. That is, seeing was enabled by movement and was hindered by being kept still. Now, we're moving our eyes all the time, and the eye movements you're most familiar with are when the eyes dart from looking in one position and look at another position. Those are called saccades. And we have devices called eye trackers that can closely follow where the point at which you're looking changes as you, for example, scan an image. So here you can see an eye tracking registration of where someone looked as they looked at this photo of a female face. And there's a well-known pattern here. For example, the eyes dart around, picking out important details. They'll gravitate towards the eyes and the nose and the mouth, and they won't spend much, if any, time at all on the background. Now, a saccade is a relatively quick jump from one fixed position to another position. And we're doing these all the time. That alone would be destructive for any camera, but there's a lot more. One kind of movement the eyes do, which is a bit unusual in that it's the only eye movement the eyes do in which they don't move in parallel. As something comes within a narrow area around the body, the two eyes move in towards the center line. This
Stay focused on the tip of the Q-tip. Very good. Very good. We're going to do one more time. You can see the convergence in the pupillary constriction.
So that's another weird kind of movement eyeballs do. They move in together. Now, here's an interesting thing about eye movement. If I hold my finger up and I move it around like this, I can follow my finger. I think you'll see I'm following my finger successfully, smoothly. I can't do that if the finger isn't there. My eyes will jump from here to here, but they won't be able to move smoothly unless there's something in the world for them to follow. This is called smooth pursuit movement. This gentleman will illustrate it now. So that's a kind of eye movement you can only do if the world cooperates. It's not under your control. It's a relationship between the eyes and the world, which is held steady as the things in the world change. That's smooth pursuit movement. But we have another way of keeping the relationship between the eyes and the world steady. This time, if it's not the world that moves, like my finger, but my head. Notice that I can also keep my eye on my finger as I rotate my head. This is called the vestibular-ocular reflex, and crucially involves the vestibular organ in the middle of the ear. Let's have a look. This woman is going to illustrate as her head is mercilessly yanked around. She keeps her gaze fixed directly. So this is a very important and somewhat subtle reflex, which involves the middle ear and the muscles that cradle the eye. Now, as it happens in birds, it's not the cradling of the eye muscles that does this, but their whole head and neck. And we can see this very clearly in this wonderful owl, who will now demonstrate the stability of that gaze. When an owl has you fixed in its gaze, you are truly fixed. This owl is terribly, terribly patient, but very, very good at keeping its gaze laser focused on the world. Sorry, I've seen this owl so many times, but I still love him. So we've got the saccades. We've got this relationship between the gaze and the world. We've got vergence. We've got one more. Tremor. The eyeballs are always shaking. They have a built-in shake, tremor, at about 80 times a second. Your eyeballs are vibrating. It's very low amplitude. It's physiological, and there's something wrong with your eye if it's not doing this. And we have no idea how to incorporate this into our theories of seeing. So there's a lot we still don't understand. But together, this makes it quite clear that the structural similarity of the camera and the eye is a bit misleading, because the business of seeing that the eye is involved in is a much more complex business and involves activity. So the body of the eye is not unlike the case of a camera, and the lens and the pupil bear structural similarity. But a camera, of course, does not see, and despite such talk being loosely used, there's no such thing as the sending of images to the brain. That is fantasy, mere fantasy. Images are not sent to the brain. So there is variation on the retina, which is very important for seeing, but it's not the case that images are being sent upstairs, as it were. Movement and activity are absolutely integral parts of seeing. So we'll move on now in the next video, and we're going to dive into, in the next few videos, we'll dive into the two main approaches to visual perception, which is, we'll call internalist or computational, and externalist or relational.